Okay, so we are starting with the recording. I will try to use this today. Okay, so let's discuss a couple of examples, and we will be using those Trotter-Suzuki formulas. So we saw that limit of n going to infinity of I t a divided by n e to I t not a b divided by n to power n. We saw that this is e to I t a plus b. Okay, so now I will give you a couple of examples how to use it, and we also have the stronger formula. So let's call this u n, or maybe, yeah. So u n minus u. We got a stronger formula bounding it by, I believe, t squared n, and then the norm of the commutator a b. We can recap in a moment whether this is exactly true. But roughly we have this bound, and if I don't know if there's a 2 or 1/2 somewhere, then I can just write this notation, O of t n, and if I write O of t squared, so in this case I would write also O of t squared over n, and sometimes we would also write O of 1 over n. So to recap, this would mean that if I write something like this, then there exists a constant such that this u n minus u is bounded by this constant t squared over n. And if this is the exact bound and I didn't forget like a factor of 1/2 or 1/2, I can forget. 2 I shouldn't forget, so maybe I put a 2 in case I forgot it. So I'm just increasing the upper bound here, right? And there's something. Okay, no, nothing in chat. If there's some questions, just interrupt me. So if I write something like this, then there exists a constant such that this, and we see that in this example here, I would have that my constant c would be 2 times a b commutator taking the operator norm of this. Okay, so that this is called the big O notation. And same mode as before, if I write something with words, it means that there's a good Wikipedia article for this, worth checking, okay? So, and one thing that is useful, those are tutorials to tell you, what is this transition? And this transition means that, for example, we will keep t, if I am doing this transition, then it means that I'm keeping t fixed, and interested in changes in n, in capital N. So if I would be writing O of 1 over n, then I would have the bound u n minus u. I would have a new constant c prime t, not t squared, 1 over n, and c prime would be then, t would be kept constant, yeah? T times ab. Okay, so that's the difference. Whatever is kept inside of the argument of this big O notation is something that you're interested in scaling it. For us, strictly speaking, it would be n, but t is the evolution time, so sometimes we will write those expressions like this. It's because we want to know also what is the additional dependence on t squared, okay? So those are the constants. So we have this bound. So example number 1. Let's say I have a superconducting qubit, and then somehow I couple it to some drive. Okay, and let's say that this drive, if I do it correctly with some ground and so on, and then maybe there's some ground here as well, and then if I do it correctly, if I switch on some time-dependent voltage here, then it will amount to some time-dependent omega of t evolution z sigma z operation. Okay, so in my case, my operator A would be omega of t times z. That would be some, just to give you a sketch what would be happening. And that would be some time dependent of evolution. But if I do a pulse like this, I could say, okay, I switched on a sudden evolution. So this would be maybe still time dependent. But if I apply a pulse like this, so this would be the voltage, this would be some time, then effectively you could derive that maybe I have some time tau times z. Okay, and that would be some unitary UA, and in this case tau times z would be my operator U. Okay, now if I would have some coupling to some maybe some other element, and those are just sketches, I'm not saying that such a quantum circuit would work. If I would have this coupling and I would modify the frequency of this, then I could suddenly put those two qubits onto resonance. So maybe I would have another operation, and that wouldn't be exactly that operation, but let's say I would have an operation of the type tau, maybe eta x tensor x. Okay, so that would be a 2-qubit operation. And for example, I could do this kind of pulsing on both qubits. Okay, so so in this example, my operator B would be eta x tensor x, and here I could do now 2 qubits. So I would maybe do z tensor identity plus identity tensor z. I will rewrite it in a moment. So in the case of twice independently here and here, doing that operation, I would have z tensor identity plus identity tensor z. Okay. So now the first operation is that we could use that formula. So e to ia times e to b divided by n to power n to approximate the evolution e to I tau z tensor identity plus tau identity tensor z plus eta x tensor x. Okay, plus some error, and we know that the norm of this error is O of n to -1. Okay, so that's a first application of what's going on here. And this is something we could call a Hamiltonian simulation. Which means we have from simple ingredients. I don't know if there's a good Wikipedia page for Hamiltonian simulation, but from simple ingredients, get interesting evolution. Okay, and so the Strotter-Suzuki formula is the first example of quantum compiling that we get. Okay, there's the Hamiltonian simulation Wikipedia link. It exists. Very good. So I will need to check whether it's actually good, but there could be different definitions. But basically, the idea would be that from small changes and time-dependent operations on the system. So you see what kind of control physically we would have. We would be changing voltages on the individual qubits. Somewhere here would be also a coupling to this. And we would be changing the frequency of the coupling element between the qubits. So that way we would physically have an engineered time-dependent evolution. And if we switch this on and off in the right way, we will get this joint evolution. And it's not so obvious that this happens, yeah? And we kind of proved this formula here. So, so we could say that Hamiltonian simulation is a way of using gates. So our gate number 1, or in Hamiltonian simulation, we would say that we use the ingredients are those are Hamiltonians. And interesting evolution or Hamiltonian would be target Hamiltonian. So the tutorials are more or less about methods, but it's still a tutorial. So so going away from the mathematical methods, let me give you one example of a Hamiltonian. So I know, but I will need to introduce a lot of notation. But basically, we can consider Pauli operators at different positions. So maybe Z, J, and some magnetic field J in some lattice lambda. And then we would have Ij in the edges of that lattice here, and maybe we would have Xi, Xj interactions here. And that would be a model for a quantum magnet. And then we could ask about the evolution of this and so on. So the idea would be that we have some lattice maybe physically, and then by having those couplings like I sketched above, you would be switching on and off maybe voltages here that are steering the coupling on and off, and you would be adding artificial magnetic field in Z here. And that would be a very physicsy application to simulate the dynamics of some quantum magnet. Okay, how those couplings work? This is on arXiv quantum engineer's guide. Engineer's guide to superconducting qubits. Okay, they really explain this on 20 or 30 pages, how those voltages will translate. And then you can imagine if you have a good hardware, you can do this operation where you have some big Hamiltonian, some interactions between qubits, and some on-site voltages here. Okay, so that's one idea, which means that we would be using quantum hardware to simulate the dynamics of some quantum magnet that you could, in principle, find in a physical system. So that's why we stress Hamiltonian simulation, which means we use quantum hardware qubits, for example, to simulate, instead of Python, we use quantum computing, and we simulate the Hamiltonian that would be governing some quantum magnet. Okay, that's why Hamiltonian simulation here. So that's one application. And now let's talk about quantum compiling. And the first example to quantum compiling will be Hamiltonian simulation. So let me define gate number 1, which is E2IA, and then gate number 2, which is E2IB. And let's say I can do this with a smaller argument, 1 over n. Then we see that I can use those two gates. Those are two quantum gates, which means those are just quantum operations. And if I interlace this, I will get A plus B plus our error operator, okay? Which means that if I have those operations, I can put them together to get a more complicated operation. And in our example, we had Z, then X tensor X, and then we repeat this, right? Z, and that was the evolution under Z, and then X tensor X all together. This is just symbolic. Okay, which means that we were able to, and basically this is repeated, right? Like this. Okay, so this is this n. And this is why we are talking about compiling, because we have two qubits here and we keep applying operations to it. And basically we wanted to apply this operation to the two qubits. And instead we were just applying those gates. So we compiled a circuit. We would say that we compiled a circuit here. And that solved the problem how to apply this evolution to our system. Okay, so that's quantum compiling. Now we can do more complicated things with compiling. So for example, let's say I have n gates and the kth gate is E2I AK divided by n. So what can I do with those gates? Basically, Trotter-Suzuki decomposition tells us that if I take the product G until m, maybe I have k from 1 until m. If I repeat this n times, I can get the evolution summation ak, k from 1 until m. Okay, so that's and the important thing is that in the argument here there was n, but we did this n times, so there is no n here. Okay, so so the second example is larger sums. Okay, so the next operation that I want to describe is the group commutator. And the group commutator is the following formula: E to IA, E to IB, and then something new comes in because we cannot endlessly just concatenate such operations. We need to do something interesting. And the interesting bit is inverting the evolution under A, and then we also invert the evolution under B. And what is this? This is the evolution under I1/2, the commutator of AB, plus some error operator of this group commutator. So now we were talking a lot about notations and so on. And what we can prove is that if I consider this group commutator circuit, it's a small circuit, right? I have plus A, plus B, minus A, and then minus B. Okay, so I'm talking about the generators AB minus A minus B, but I could also call this VA, VB, and then VA dagger, VB dagger if I want to the boxes to indicate unitary operations on the qubits. Okay. So this is the concatenation here. And now we could ask what is GC, maybe some brackets like this, minus e to I 1/2 commutator A B norm. And this is exactly the norm of our error operator GC, which is just defined as the difference. This equation just defines it. And here we can prove that this is 1 over square root n. I think that was the bound, if I'm not mistaken. Yeah, I think so. That was this bound. It's a little bit slower. So let me just tell you what I mean now that this is slower. So if I have O of n over 1 versus O of n to minus 1/2, which one is slower? Yeah. So if n is 1, 4, 9, 16, then here I have 1, 1 over 4, 1 over 9, 1 over 16. And here I will have 1, 1/2, 1/3, 1/4. Okay, so basically here the error becomes larger. And why the error becomes larger is because we have a cancellation. So let's just talk about the cancellation in a moment. So the error, we could say that the compiling error is larger because of cancellation. So a few things to say. This formula is simple to understand. We can understand it in a moment. To derive this is not so simple. I will post the link to my paper where I do it with the interpolations, and we would have to spend 1 hour to derive this. So I'm not doing it right now, but we understand the norms, and assuming that we have this result, we can start using this. And I want to show you how to use the group commutator because it's a tutorial, not a lecture. But we might come back to it, and it would be a little bit more of a lecture to be showing those bounds again. But now I was trying to explain that if this result is with 1 over square root of n, then the bound is a little bit less tight. Okay. So let's pretend that let's do the group commutator when A commutes with B. Okay, so as a reminder, e to IA, e to IB, e to minus IA, e to minus IB. And this, when everything commutes, is A plus B minus A minus B, which is e to I times 0 is the identity. So this is the left-hand side. And the right-hand side, we said it's I 1/2 commutator AB identity. So the error is 0 in this special case. Now, if it's not 0, then we get something more interesting. So let's consider A is Z tensor identity plus 1 tensor Z, and then X B will be X tensor X. What is the commutator of A B? This will be can we do it in a simple way? Not really. So it will be zx tensor x plus x tensor zx, and then minus x tensor xz minus xz tensor x. Okay. And this is just a complicated matrix. So let's call this matrix C. Okay. I cannot really simplify much. One exercise to do is that zx is proportional to sigma y. So my Z matrix again is 1 minus 1, 0. X is 0, 1, 1. And then Y would be 0 minus I, 0. So you can work out what's the proportionality constant, that doesn't matter. And this symbol here, there's a very good Wikipedia page, it's the Kronecker product, yeah? Which means that dimension of C is just a 4x4 matrix, okay? This is not very complicated stuff, I hope. So this is just to have some specific examples, but you see we get a complicated operation here, okay? So now we could be designing other operations which are in some way canceling something somewhere, okay? So I will explain this in a moment, but now I would like to say that this C is a new operation, okay? So we could, for example, consider e to I a over n, e to, so using the C operation, I could consider e to I b over n, and then maybe e to c over n, 2 power n, and then I will get approximately, I will get e to a plus b plus c, okay? And now how to do this with e to a, b, c, and so on. So I have to have e to I over n, e to I b over n, and then, for example, e to I n, 2 times this maybe, this operation squared, because I want to remove the 1/2 later. Okay, let me put the 1/2 there. The 1/2 is important, yeah. 1/2 here, e to a, e to b over n, e to minus I a over n, e to I b over n. Yes, and this we repeat to power n. Okay, so that's our approximation. The difference here is that we use this new operation here, which involves the evolution inversions 4 times here. And what it turns out to be doing is it's adding this component of the commutator into the evolution. And so this becomes a more complicated operation, EA plus B plus commutator AB. Okay, and if those are simple operations, then this becomes complicated, right? So this is how one could use some compiling step. If this would be our target evolution, we wouldn't be doing this because we don't have access to this, but we get access to this through this group commutator formula. That's our group commutator formula here. Okay. So, and why is this important? Because I wanted to have something here like that. Okay. So another question is, how general is it? And the answer is that this is exactly what it means to have a universal quantum computer. So we say that a gate set K in K is universal if there exists maybe J1 until JQ in capital index at K, such that G1 GJ1 dot GJK. So JQ. I apply those Q many gates together. If for all epsilon larger than 0, maybe I have some unitary here, and I can approximate this unitary up to an epsilon, for example. Yeah. So basically, I can put those gates together to reach an arbitrary unitary U. And the way we would be doing this is by considering maybe some general compiling schemes that I will not explain now. Or we can try to explain this with the formulas that we know now, assuming something that we usually don't know in quantum computation. So let's say I have a unitary U, and we know that a unitary group on N, which is all matrices N by N. Okay, maybe I should be using D, because N today is how many Trotter steps I'm using, such that M inverse is equals to M dagger. That's one way of saying this. And then I can erase this. And what I meant to say there is that for all unitaries, or maybe I will use V, for all V in the unitary group, there exists H, which is self-adjoint, such that E to IH is precisely equal to V. Okay. And now the point is that that this set GK is universal. Equivalently, if GK is of the form E to IHK, such that the commutator algebra, so HK prime, if I keep nesting this and so on, the span of all such nested commutators becomes all Hermitian matrices d-dimensional. Okay, so let me explain what I mean by this. So we need to understand what happens if I want to compile an arbitrary unitary. I want to assume that I know it's Hamiltonian, and then there is a result in linear algebra that you can use, which says that if you form commutators, let's call those commutators I don't know, C, and then K1, K2, and so on, Kn, which will be HK1, HK2, dot, and here we were using Q, HQ, and so like this. Then if I take sufficiently many, then all possible linear combinations. So if I sum over those k's, and I take some lambda k, c, k, then I can write any matrix H in terms of those matrices. Okay, so to give you a picture, if I have a three-dimensional space, then I could have also a non-orthogonal basis. So maybe something like this, that basically they are not orthogonal, they have a small angle, and then I could maybe orthonormalize the spaces, and our CKs, CK maybe prime, are such a non-orthonormal basis, but at some point, if I take sufficiently many, then they will allow me to write any Hamiltonian in such a non-orthonormal basis. Okay? Okay. So if I assume that I have my Hamiltonian in this form, we know exactly what to do, right? Because what I want to do is to write e to IH as the product. So let's say I have K1, CK, and then I here, because of this I, K1 here. And I leave some space because there's something missing there. And if the notation is not too confusing, then you should be able to understand what I mean here. And then dot, 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 e to I alpha k, k maybe m again, or I don't know what's a good, k maybe capital J many operations like this nested commutator of some type. Okay, and then I need to do Trotter-Suzuki decomposition. So I need 1 over n. Okay, so we have this chain of reasoning. We have a proposition for any h, there exists k1 until kj we were writing, kj, such that star holds. Okay, so this proposition is a linear algebraic argument, and it involves linear independence on a vector space. I didn't prepare you to understand this, but I will write this, and if there's feedback that I should explain this, I will explain more. Proof linear independence of something that we will call commutator algebra. Okay. Why is linear independence important? It's because I have basis vectors. I have some coefficients alpha k, which will be, let's say, I think in general they have to be complex. So yeah, they have to be complex, but we have those numbers. We have those numbers that are just coefficients. They play the role of the time of an evolution under this kind of interaction. And then we keep changing this interaction as we go. And linear independence means that in those basis vectors, I expand using those coefficients. I sum it together as a linear sum. So it's a linear superposition, and I obtain my target Hamiltonian. Okay. So if I have my target unitary U, or I think I was writing V, and I want to compile on a quantum hardware this evolution, then I could do it by asking what is the decomposition of the Hamiltonian into the commutators, into nested commutators. And then once I know the commutators, I use Trotter-Suzuki decomposition to decompose the problem into compiling e to alpha k, ck. Okay, and what does it mean? It means that I have e to some number alpha k, and I have nested commutators. I have hk1 with hk2, close this one, and then this commutator is commuted with hk3, and in general until hkq. Okay, so we have let's say q many commutators here. Okay, but what we can do is it means that we have to use a group commutator formula q times. Okay, and if you already trust this, it means then that we compile using gates e I h q divided by n, or maybe some number n bar with some arbitrary phases. If you have arbitrary phases here, compile using this, and arbitrary v e to I to power h. Okay, so why is this a good example of Trotter-Suzuki decomposition? Because it's an inefficient but a very intuitive way of explaining. If you would ask me on my powerful quantum computer to engineer this kind of evolution, I would have to understand many things and so on, but I would know how to use Trotter-Suzuki decomposition to start with simple gates, very simple gates, which are just maybe some small interactions here and there, to engineer any evolution. Okay, so because it's a tutorial, I will not finish the thing, but example of universal gate set would be single qubit rotations I b sigma. Okay, so e to I b x x plus b y y plus b z z for arbitrary v in R3 and an entangling gate. Okay, what do I mean by entangling gate? It means that if I have a state 0, 0, and I apply this entangling gate epsilon to 0, 0, I get a psi, and psi is entangled. So entanglement is a resource for certain types of quantum computations, and in some way this is a different type of information in some way, or correlation that makes the quantum computer different from a classical computer. So I will give you an example of this entangling gate. So example of entangling gate, epsilon would be 1, 1, 1, not minus 1, 0 and 0. So it's a unitary operation on 4 qubits. Okay, and what is important is that sometimes I'm switching. So if I have many qubits, if I have L many qubits, L qubits, then it's understood that if I apply my G of B gate on the nth qubit, then I just apply it on the nth qubit, and I apply identity on the rest. And if I apply my so this is actually called CNOT. C naught. If I apply a C naught between the first and the last qubit, then basically those two qubits could become entangled by the action of that gate, and the rest of the qubits, they just get an identity. So this C naught I can apply between maybe the second and third qubit, or the first and fourth qubit. So we denote it like this. In circuits. I'm not explaining the notation today, just telling you how it looks. Okay. So basically, you see that those are operations that involve two qubits at a time, or one qubit at a time. Maybe I would apply GB prime here and G double prime here, and so on, and then maybe a new C naught, and so on and so on. Okay. And so in this paper that I'm not citing here, this is a result from 2000s, like 20 years ago. People have studied this, and they showed that, for example, early on, already I think in the 90s, people understood that C naught and single qubit gates are universal for quantum computation, which means that I could use those gates, this plus my C naught here, I could use them here. I could form all possible commutators here. And then if I form those commutators in all possible ways, I would be able to compile any unitary. That's what it means that I have universal gate set. Okay. Then later people studied it more, and they understood that all that you need is single qubit rotations and anything that entangles a product state like this. If it entangles a product state, then it can be this C naught operation, but it doesn't have to be. Okay. So we have quite a lot of flexibility, and I'm not proving this today. It's really like an overview tutorial. But you kind of see why we have this flexibility, that anything, it doesn't need to be so beautifully structured like C naught, which is very useful, and it's easy to make sense what it does. It could be any entangling gate. Why? Because once we start forming those commutators, we get new dimensions coming in. So here I would need normally 2 to power L order of 2 to power L operations, and I have L types, I have order of L single qubit rotations, and then L maybe squared how many qubits I will choose, right? Because L choose 2 qubits, and that's the number of C naughts that I have essentially, right? So this is poly in L, which is my gate set. It's a small gate set. And in principle, I can reach this dimension here of how many operations I have. This is very scribble. But basically, the gate set is a very small set of operations. But once we start creating commutators, it becomes an independent operation. And let's look here why this is an independent operation. Here I have this matrix C, and if I would like to write it as alpha Z tensor 1, or maybe A, plus B identity tensor Z, plus small c x tensor X, then I will not be able to find A, B, C such that I write this as a linear combination of this, which means I got a new type of operation, which is generated by my new matrix C, which is the commutator of A and B. And that operation is linearly independent from those. Just by inspection here, you see that this is not the same matrix, okay? And then if you generalize this, there's a lot of work, and you need to have good notation. Today I have a very bad notation. But if you generalize this, then nesting those commutators creates at some point linearly independent set. which means that there will exist a combination of those commutators so that I can express everything here, okay? And we can have any entangling gate because getting linear independence is easy, okay? It's just add the dimension. Once you have the dimension, you're in the game, okay? The problem is that it will not be a very efficient or practical operation, and it will be hard to compile it because you see that here I would have to make many of those operations. Okay, so that's the story of universality and so on and so on. Okay, I may be repeating myself many times, but I will just maybe recap in a moment. I just want to explain still one more thing. Let's say I have example. Okay, I will have two more examples and then I think I want to finish. How to get so there's one question in the chat. What are other entangling operations that are not a C node? So a C node we can create. It's a yeah. Okay, actually, wait. C node. That's a good question. So CZ is what I wrote just now. 1, 1, 1 minus 1. That's another very common operation. A C node is actually, I wrote it incorrectly here. A C node would be a matrix which is off diagonal. So 0 here, 0 here, 0, 0, 0, 0, 1, 0, 0, 0. Okay, I will rewrite this. So CZ and C node are related. It's an interesting homework. What's the relation between them? 0, 0, 0, 1, 1, 0, 0, 0. That could be taken as the C node, for example. Okay. Why is this an entangling gate? How to explain this? That would need maybe a tutorial on entanglement. But basically, if I start with a 0, 0 state and I apply any evolution of this type ZZ plus maybe Y tensor Y with some angles A, B, C, and I apply it to psi, if those A, B, C are non-zero, then psi is entangled. So for 2-qubit entanglement, there's a lot of tricks that you can do, and it's actually quite a pleasant game in basics of entanglement theory. What we would need to show this result would be a few ingredients. We would need SVD. We would need the Schmidt spectrum. Are there any bounds tension? So entanglement is a question of the type yes or no. Okay. And if I would apply the entropy, I could measure how entangled it is. And C node and CZ are special because very easily they create maximum entanglement between 2 qubits. That's why they are special. And they create Bell states. So I'm writing it down because the Wikipedia for this will be very rich. So using SVD, we can do the Schmidt decomposition. And then we could define local unitaries, local unitaries. Okay, I will write LU for local unitaries. And then the Schmidt decomposition gives you something called Schmidt spectrum. Is invariant under LU, and then you can see that those entangling operators, they would be, for example, of this form with ABC not non-zero. You could prove that this is an entangling operation for arbitrary non-zero ABC. Yeah, so that could be an exercise. I could maybe formulate an additional session for this. It's a very nice exercise. And basically what the interpretation of this is that entanglement creation is generic in the sense that you don't have to worry about those angles so much as long as you entangle. And then as long as you entangle, you could use the group commutator many times. And at some point, you will pick up enough dimensions so that you can express any operator. And then voila, you have a universal gate set in hand. Okay, that's the good thing. That's the nice message. That's something that was very nice theory, and top researchers in quantum information were deriving those results, that you don't need the C node or something. Any entangling gate would suffice together with single qubit rotations. Okay, that's the good message. The bad message, and that's the questions in the chat, I think. The bad message is that if I use some whatever operation A, B, C, then it might be difficult for me to know exactly how to put those group commutators together. That's the bad message. That I have to know precisely what's my entangling operation in order to be able to specify some order, how to order those group commutators, and how to get my compiling straight. Okay? In the scheme that I described, but in general also like that. Okay? So there's good and bad messages. The good message is that it's fairly easy to get a universal quantum computer. The terrifying message is that you need to know what you have in the lab, and it's not easy to know. Okay. If you're asking, okay, maybe I will use other entangling operations. Maybe I will not use C naught CZ, but I will find some magic angles pi over 15, and my favorite number is 0.123 for ABC, and that's my favorite gate, and I will use this to build my universal quantum computer. You can do this, but you need to be able to translate this into quantum algorithms, which is possible. It would be another tutorial, but it's adding some complications on top. Okay, so the possibility is not the same as practicality. That's maybe the comment here. Okay. So one last example that I want to give is, wait, what did we say? So this example was explaining that we can have a very simple universal gate set. So for example, a CZ operation acting on 2 qubits and single qubit rotations, you keep applying them together and you will be able to engineer any operation on n qubits. Okay, thanks for the messages in chat. We just do one more example and then probably finish. So let me explain why something like this might be non-trivial. Let me take H1, which will be X tensor identity. H2 is identity tensor Y tensor Y. Okay. Okay, actually, I want to do 2 examples, but okay. So what's the commutator H1, H2? This will be X tensor X, Y together, tensor Y, minus X, X tensor YX tensor y. And using this associativity of the tensor product, again, associative prop of Kronecker product on Wikipedia, xy, and we know what's the commutator of xy, it's z. So we get something which is proportional to x tensor z tensor y. All right. And why is this interesting? If I have physically, in physics, if we have three spins and they exchange some photon, then maybe they couple in x tensor x. And usually two particles interact with each other, but not three particles interacting with each other. So you see that using this, I got a new Hamiltonian that is much more exotic because it has three sides interacting together. Okay, so that would be the meaning of taking e to IH1, e to IH2, e to minus IH1, e to minus IH2, then divide by n, take this to power n, and your homework would be to understand what's this 1,2 Hamiltonian, right? So I kind of solved it for you, but you can ask about the constants here, and you can ask about the error operator. Okay, so that's my example. The group commutator on 3 qubits gives me a new operation. There's no way I can write this as a linear combination here, and then I get those qubit rotations, right? So that's one example where you see that if you started from something already a bit more complicated, then using the group commutator here, we can make it even more complicated, right? So I will have here e to some q times x tensor z tensor y. A very funky Hamiltonian, very, very funny stuff, okay? So now let me explain how to get H1, H2, H3. And next week we will need to do some discussion of how to inherit bounds. So W12 will be e to I H1, e to I H2, and maybe of some epsilon, e to minus I H1, here epsilon, e to minus I H2 epsilon. And so now if I want to get the evolution under this C1, 2, 3, so e to C1, 2, 3 would be that I can call this H1, 2, H3. Actually, better notation that I was trying to use before is to use the star product here, H3, or no. Nah, forget this comment here. Actually, maybe not so much. Maybe I could use the notation if the comma is kind of annoying. 1 star 2 and H3. Okay, this is just indicating where I'm putting the commutator, either comma or star or something. So how would I do this? I have this commutator generator here. So I would make the group commutator here with I H1, H2, e to IH3, e to minus IH1, H2, e to minus IH3. And I'm not very careful about some phases, so maybe there will be some A, B, 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 maybe I need to there was this 1/2 problem there. Okay, so this will be e to I 1/2 commutator h1 comma h2. Because of this 1/2, maybe I need this b and a. So how do I do this? E to I h1 and then if we want here some epsilon squared, maybe epsilon squared, epsilon squared, epsilon. E to IH1, E to IH2, epsilon, E to minus IH1, epsilon, E to minus IH2, epsilon. Then E to IH3, epsilon. And then I won't repeat this. I will just write 1,2 of epsilon, dagger, E to minus IH, not H bar, 3. Okay. So my point here is evolution governed, this is not on Wikipedia, evolution governed by a nested commutator can be obtained by nesting the group commutator. Okay, and with this we are more or less done, because that's what I wanted to say. We want to have evolutions governed by nested commutators. Okay, and for this we will be nesting the group commutator, because the group commutator is an operation, and if I nest this operation, I get new evolution. It's governed by something, and it's governed by this nested commutator. Why? Because I have the C1 to 3, which is 2 commutators nested together. And the way I could do this is I could nest it once to get this first innermost commutator here. Okay. And then what I could do is I could nest this evolution into the group commutator in this way. Yeah, those are only operations, that those are just simply operations. Yeah. And the way it would look is that ultimately I would have H1, H2, H3 in different orders. Okay. But if I align them in the right way, I will get in the end an evolution under the C here. Okay. What I didn't explain is that, for example, here I will have to lose the I, because this is anti-Hermitian. So there's some things to keep in mind. And also, if I did an evolution here according to epsilon, then I will get epsilon squared here, maybe with some 1/2 constant here. Okay. So if I get a dilution of my time from epsilon to epsilon squared, there's something I will need to be have to do about it. And that's exactly what we were explaining already. So what we will need to do about this will be the Trotter-Suzuki formula, which is what I started with. Okay. Here. You see it by the n here and by the n here. Whoop. Okay. So what do we have here? We discussed that any unitary operator is an exponential of a Hermitian operator, so a Hamiltonian. And then what turns out is that we can create a basis for Hamiltonians by taking nested commutators of certain smaller operations. And whenever this is true, then we have a universal gate set. And we gave an example of this. Any single qubit magnetic fields together with an entangling gate that I wasn't explaining too much in detail, besides explaining that it's entanglement. Yeah. Okay, so this could be, for example, the CZ operation, and then you already have a plan for how to build a quantum computer. And here we gave a proof of principle discussion of how to compile any unitary V. The problem here would be that there would be very many operations, exponentially many operations, because in general, those operations are very complicated and we have very simple gate sets. Okay, so quantum compiling is about taking simple gate sets and getting more complicated gates, circuits, and so on out of it. Yeah. So the simplest one that we discussed is Hamiltonian simulation, where we kind of try to add the generators of the gates A and B so that I get the evolution under A plus B. And because of non-commutativity, we also did the commutative case at some point, blah, blah. When it gets interesting, the non-commutative case is interesting. Yeah, that's why the quantum computer is interesting, because we get non-commutative operations. And to get this commutation into the game, we can build the group commutator. And then you can ask, okay, why not make more complicated operations out of A and B in other ways? And the answer why we go through the group commutator is because it's very simple. So I will get a more complicated operation A and B here by applying A, B, and then minus A minus B. Okay. So out of using 4 of those gates, I get a new gate, which is new. Why is it new? I mean, we had some examples. For example, if I have 3 qubits, the first to interact with X and Y, first to X and X, second Y and Y. Okay. Then if I will do the group commutator in this way, I will get the interaction under X, Z, and Y. Yeah, very nice. So that's why the group commutator is useful. And we discussed more or less a general scheme how to pull it off in full generality. Okay. Okay. So there were 2 different things. There was okay, we started with the Trotter to Suzuki decomposition. We understood the errors a little bit. And then we understood that we can create different evolutions, and I was giving the qubits examples. Then we can make the general evolution under any Hamiltonian. And to become more interesting, we said we need the group commutator. And in the next session, I will explain how to inherit the bounds. Okay. So there will be some cancellations involved, and the cancellations I actually explained because this would be exactly this if it would be commutative. Okay, and the next step was to unleash the power of the group commutator, and what we got is a universal gate set. Yeah, and I even tried to explain the only hard stuff that you need to understand is this linear independence of the commutator algebra, and that's where Lie algebras are useful to understand. Okay, and that's something that I didn't have time to explain. But once you assume that you can decompose the Hamiltonian into commutators, then you can use the Trotter-Suzuki decomposition to go. And then once you have this Trotter-Suzuki decomposition n times here and so on, then you can look at the individual terms. And then later I was explaining how to do the individual terms here. That was this discussion here. Okay, so that's the complications of quantum compiling. Very good. Okay, let's finish here.